In this video, I'm going to describe how to divide polynomials using a long division technique. But before we get started doing polynomials, let's recall how just plain old long division back from elementary school goes, because I know it's not a skill that people use all the time. Suppose that I was looking to divide 7,802 by the number 21. For our standard long division algorithm, in the US at least, we set the problem up with the numerator, the number that's being divided, under this radical bar, and then the number that we're dividing by goes out front. It's important to remind ourselves, so maybe I can even write that this number is the numerator. And then we proceed with long division. And the first question that we ask ourselves, because this is multi-digit long division, we say how many times does 21 go into this 78? And of course 78 is actually shorthand notation for 7,800. That's what we're asking. So how many times does 21 go into 78? It goes in 3 times, and really this 3 is in the hundreds place, because 21 goes into 7,800 300 times. And our next step, we multiply this out and we see that we get 6,300, which we just write as 63, and subtract, and 8 minus 3 is 5, 7 minus 6 is 1, and this next step we, as notation, bring down the 0. What's going on here? Really, now that we've taken out 300 of these 21s, we're going to see how many 21s do we need in this tens place. So how many times does 21 go into 150? Well, I'm just thinking in my head, 2 times 7 is 14, so 21 times 7 is going to be 147. And again, these are in the thousands, the hundreds, and the tens place, but for our algorithm, we don't worry about that. We do the subtraction again. 0 minus 7 is not possible, so I regroup, change this to a 4. 10 ones minus 7 is 3. 4 minus 4 is 0, and 1 minus 1 is 0. And our final step, well, almost final step, I bring down this 2. And now we're looking at 32. This actually is 32, 3 tens and 2 ones. I'm going to say how many times does 21 go into 32? It goes in 1 time. I'm left with 21. 32 minus 21 is 11. And so maybe in elementary school you typically wrote this as remainder 11. And what does that 11 remainder actually represent? It represents 11 21sts. So our final solution is that 7,802 divided by 21 gives us the value 371 and 11 21sts. I'm writing this as a mixed number, the whole number part and the fractional part, the part that's left over. So although polynomial division isn't identical, it's very similar in the algorithm that I'm going to do. So this is sort of a long, messy problem, but I think it gives us a chance to see all the pieces. Let's say I have x to the 4th minus 5x cubed plus 2x squared plus 10x minus 5, and I'm going to divide that all by x plus 2. Recall polynomial division, these are both polynomials because they're both a sequence of terms, each of which has a numerical coefficient and an x raised to a power. So let's set it up the same way that we saw before. I'm going to set up this fraction bar. Recall that the numerator is what goes under this fraction bar. So this is x to the 4th minus 5x cubed plus 2x squared plus 10x minus 5 is all being divided by x plus 2. This looks a little overwhelming, but we're going to take it term by term. So the first thing that you think to yourself is, I'm going to compare just the leading coefficient of the numerator with just the leading coefficient, or the leading term of the denominator, the leading term and the leading term. And in this case, I ask myself, x times what is equal to x to the fourth? Or alternately, x to the fourth divided by x equals what? I think multiplication is easier for me to think about in this. So let's write out in red. What am I thinking for this number? I'm thinking x times what is x to the fourth? And I know that x cubed times x is x to the fourth, so I'm just looking at my leading terms to answer that question. Now that I've decided that it's x to the third, my next step is to multiply x to the third by this entire polynomial. So I end up with x to the third times x, which is x to the fourth, and I also end up with x to the third times 2, which is 2x to the third. So I'll write that in green as my next step. So this step here, maybe I can even label these, but this step here is the step x plus 2 times x to the third, and it gives me this polynomial. So just like the standard algorithm, I take these numbers and I subtract this polynomial, and I'm adding parentheses. Like looking back on our old algorithm, when we took 78 and we subtracted 63, it's easy to know that I'm subtracting both the 3 and the 6, but sometimes when dealing with polynomials we forget that I'm subtracting both the x to the fourth and the 2x cubed. So let's perform this subtraction. X to the fourth minus x to the fourth is 0, which is good. That's why we chose this term up here. Negative x to the third minus 2x cubed, keeping track of my signs, that's negative 7x cubed. Great! So we've completed the first round of steps, and now we're going to do that same set of steps over and over and over again. So the next thing, just like before, here we asked x times what is x to the fourth. Now I'm going to ask x times what is negative 7x cubed, and that's going to be negative 7x squared. So maybe I'll highlight what I'm thinking in red here. I'm thinking of this term now, not this one up here, because I've already subtracted 2x cubes from it. So that's our red step. Then our green step is to do our multiplication. So I'm going to multiply x times negative 7x squared, and that gives me negative 7x cubed, which is what I wanted. And I also have to multiply it by the other term. Negative 7x squared times 2 is negative 14x squared. I'll write in green. What did I do here? This is x plus 2 times negative 7x cubed. Maybe I should use a different color. Different color. Here's blue pen, although it might not show up very nicely. Just like in long division, whoopsie, I put my arrow too long. I bring down this 2x squared because I want to know plus 2x squared. And now I take this whole thing and I subtract it. So what am I subtracting? Negative 7x cubed minus a negative 7x cubed is plus a 7x cubed, which gives 0. I have to subtract this term as well. 2x squared, I brought that down from up here, minus a negative is plus 14x squared, ends up being plus 16x squared. So round 2 is complete. Let's do round 3. Highlighting in red, we say x times what is 16x squared? That's going to be 16x. Then I multiply this times this to get my next set of terms. X times 16x is 16x squared. 2 times 16x is 32x. I know I want to subtract this, so I bring down this 10x for the subtraction. 16x squared minus 16x squared is 0. 10x minus 32x is negative 22x. Final stages, I ask, highlighting in red, x times what is negative 22x? That's negative 22. Now I multiply x plus 2 times negative 22, and I get negative 22x minus 44. Bring down the 5, I guess bring down the negative 5 so that I can subtract. And I get negative 22 plus a negative 22 is 0. And then negative 5 plus a negative 44 is actually plus 44, which becomes plus 39, because that's actually 44 minus 5 is 39. But we're done. What is this 39? At this point, we've done all of our division. This 39 is our remainder 39. And how do we rewrite our remainder? We rewrite it the same way that we did with our original problem, that our solution in this case, our original problem, x to the 4th minus 5x cubed plus 2x squared plus 10x minus 5, all divided by x plus 2, ends up being this polynomial plus 39 divided by x over 2. We turn that remainder of 39 into a fraction. X cubed minus 7x squared plus 16x minus 22, oh no, I ran out of room, plus 39 divided by x plus 2. Our remainder becomes this fractional piece. I should have written that on a new line. So that's my long method of polynomial division. We're going to do one more example, one that looks easy but ends up being sort of complicated. It's one in which I have missing terms. So setting up our division, I'll set it up incorrectly and then you'll correct me in a second. The numerator goes under the division symbol, and we can follow the steps that we did before. X times what is x cubed? X squared. But when I multiply this, notice that it's not going to line up correctly, that I'm going to get x squared times x is x cubed, and x squared times 1 is x squared. And now when I subtract, I shouldn't have 2 minus this. My place value is off essentially because I'm missing the x squared term. Really what's hiding in this polynomial, this could be rewritten as x cubed plus 0x squareds plus 0x's minus 2 divided by x plus 1. That when you don't have coefficients for each of the degree powers, it's best to replace them with zeros. So I'm going to take this and say that this, according to our algorithm, doesn't line up well. There are ways to work around it, but I think that this is the easiest way to work around it. So now that I have all of the different powers of x represented in this polynomial, I can compute this using the same algorithm that we did before. X times what is x cubed? Is x squared. Multiplying x squared times x plus 1, I get x cubed plus x squared. I subtract. X cubed minus x cubed is 0. 0 minus x squared is negative x squared. And we do the next step. X times what is negative x squared? X times negative x will give me negative x squared. So now go ahead and compute that multiplication. X times negative x is negative x squared. 1 times negative x is negative x. I bring down 0 x's and subtract. Negative x squared minus negative x squared is plus x squared, which is 0. 0 minus negative x is plus x. In my final step, I ask x times what is x? That's just 1. I do the multiplication and I get 1 times x plus 1 is 1 plus x. Let's bring down this negative 2 and subtract. X minus x is 0. Negative 2 minus 1 is negative 3. And I get a remainder of negative 3, which I will rewrite as a fraction. That means that this solution, x to the third minus 2 divided by x plus 1, becomes x squared minus x plus 1, and the remainder of negative 3 I'm going to rewrite as minus 3 divided by x plus 1. I could alternately write it as plus negative 3 divided by x plus 1. Both of those solutions are the same thing.